Alright, so here we are with the Chapter 7, Section 5 notes on using proportional relationships. We're going to use ratios to make indirect measurements and use scale drawings to solve problems. So, first thing we see here is indirect measurement, and it's any method that uses formulas, similar figures, and or proportions to measure an object. So we're going to end up using that idea that similar shapes have proportionate sides in order to kind of measure things indirectly. So, most of the time when we do indirect measurement, it's going to be of something that is not necessarily physically able to be measured. So, for instance, a tree, or in this case, a telephone pole. So, Tyler wants to find the height of a telephone pole. He measured the pole's shadow and his own shadow and then made a diagram. So here it is. And we need to know what is the height of the pole. So, as we know in similar shapes, we can set up proportions as long as we know that these are similar, which we do. And we can say that this base height, this is actually a shadow. What happens is the shadow comes from the sun, and it comes at the same angle here as it would be here. By third angles theorem, these are going to match up, and so they are similar shapes, and we can set up a proportion. So these two shadows are going to set up a proportion, and then we also know that the two heights are going to be in proportion as well. So we have 7 feet 8 inches. And then we have 38 feet 4 inches. And then that is going to be in proportion with 5 feet 9 inches. And a height of the telephone pole. Now, of course, none of this works out because in inches, it's actually in base 12, right? 12 inches in a foot. And so we actually have to turn all of these into their decimal equivalents. So, for instance, 9 inches actually means 9/12. And 9/12 can be reduced to 3/4, or of course it could just be 0.75. So, going back over here, we can go ahead and set up our proportion so that we have 5.75 instead of 5 feet 9 inches. The other one here, we have 8 inches, and so 8 over 12 can be divided by 4, and so we end up with 2/3, or 0.6 repeating, so we will end up with 7.6 repeating. And then our last one here of 4 inches is 4 over 12, and that's going to be 1/3, or 0.3 repeating. So 38.3 repeating. Alright, so now we're going to solve this proportion by going ahead and cross-multiplying. So I'm going to cross-multiply h times 7.6 repeating. And that's going to equal 38.3 repeating times 5.75. So 38 1/3 repeating times 5.75 makes 220.416 repeating. And that's going to equal 7.6 repeating. So we take that multiplier of 7.6 repeating, or 7 2/3, divide it out, and we get an h of 28.75. Of course, if you rounded the decimals before that, then you might not actually have that exact height, but I'm sure if you rounded, you would. Or rounded the answer you get. So in this case, again, it's 28.75 feet for the height of the pole. And so that's the idea. Basically, anytime that you have a proportion, in this case, for instance, we're talking about the shadows going in this column, the height going in this column, and then the fact that we are talking about the person, in this case Tyler, and then over here the pole. So you're always looking for kind of making that connection point for each of these. Alright, so this leads us to scale drawings, because other than physical objects that we can see, we also, if something is too big, can scale it for maps and things like that, or maybe scale models. So, if we look at our scale drawing here, a scale drawing represents an object as smaller or larger than its actual size. So we could also be looking at a virus or something, and we're kind of going to scale it up to show its detail. So, scale is going to be the ratio of any length in the drawing to the corresponding actual length. So, the ratio, again, is going to be the length in the drawing, so that smaller, for instance, if we're thinking of a map, that scale of that map, or what it says on it as the scale, and then to that corresponding actual length. For example, on a map with a scale of 1 centimeter to 1,500 meters, 1 centimeter on the map represents 1,500 meters in actual distance. And if it was 2, you'd multiply by 2, that sort of thing. So, on a Wisconsin road map, Kristen measured a distance of 11 1/8 inches from Madison to Wausau, and the scale of this map is 1 inch to every 13 miles. And so we need to know what is the actual distance between Madison and Wausau to the nearest mile. So the first thing that you would do is use this proportion that they're giving you. Of course, they've written it not in a fraction, so we do want to convert it into 1 inch for 13 miles. And then they're telling us that on the map it's 11 1/8 inch. And then, of course, we're trying to find the actual measurement. Of course, 11 1/8 we could rewrite as 11.128 or 25. So 11.125. So that we can use it a little easier when we're multiplying. So to solve this, we're going to cross multiply. Again, 13 times its diagonal, 11.125, and that's going to equal the other diagonal of 1 inch times x. So if we take the time to multiply 13 times 11.125, we're going to end up with 144.625 equal to x, because of course 1 times x is just x. And that is going to be miles from Madison to Wausau. Just to reiterate, remember that you're always talking about what columns and rows make up each of these data points. So this row, for instance, was talking about the map, and this one was actually talking about real-life distances. And then this downward column here was talking about the distance that we're trying to find. And then the scale. So you're trying to identify like what you can label each column and row in order to make sure that you haven't kind of crossed with the dimension you want to find, for instance, with this scale, because this would not work if I put 11.125 over here and 1 inch over there. It wouldn't have given you anywhere near what you needed. Alright, so then the next piece here is similar triangles. When we're talking about perimeter and area ratios, you can in fact kind of use an idea to set up a ratio that will allow you to do this without having to find measures. So, for our similarity ratio, as we've seen before, this one here, AB, the hypotenuse, would then match up with this one, DE, the hypotenuse. And so they're kind of setting up all of our ratios here. In this case, they do simplify it and make it a half. The perimeter ratio is going to be the same, because this is what I like to call in one dimension, or distance. This is also in one dimension, or distance. perimeter, right? But then when you talk about area, we're actually in 2 dimensions, right? And so what happens is, if you actually change from distance to area, you're going to end up squaring whatever it was that you had, okay? So notice that we take the half that was the scale, if you will, from one piece to the next, and we square them, and now we can talk about the area of one to the next. So we'll try an example in a second here, but the proportional perimeters and areas theorem states that if a similarity ratio of 2 similar figures is A over B, as we've seen here, 1 over 2, A over B, then the ratio of their perimeters is A over B, which we talked about, and the ratio of their areas is those 2 pieces squared. Just so you can see in this upper example here, 1/2 squared in parentheses does, of course, equal 1 squared and then 2 squared. So it does distribute that square to the top and bottom. Alright, so here's the idea. Let's say that we don't necessarily know all of the lengths of this triangle here. Okay, so we can't actually go through and find its perimeter or find its area. But if we do have a similar shape to it, which we do, right, it says it right here, that these are similar. This is supposed to be a similarity symbol. Boop. Just copied wrong. We need to find the perimeter P and the area A of QRS, so of this one over here. So, first thing we need to do is find the scale. Alright, and so the scale of triangle LMN to triangle QRT is going to be 13 over 9.1. Alright, so that's our scale, and now we can use it to find the perimeter. So if the perimeter of the larger one here is 36, that's going to go on top. Whoops, I just wrote 13. 36. But we do not know the perimeter of the other one. So how do we find the perimeter? We would set up a proportion. And notice that I haven't changed anything on my scale, because that's what I use to change when I'm trying to find area. But right now we're finding perimeter. So in order to find perimeter, we're going to cross multiply 36 times 91. Oh, sorry, 9.1. Which is 327.6. And that's going to equal the other cross multiply of 13 times x. If we divide by 13, we're going to get 25.2. And so that is the perimeter in centimeters of that smaller triangle. So now if we want to find the area, all we need to do is take that same 13 and 9.1 factoring, or scale factor, and square it. And if we square it, then we can set it equal to the area of the second piece, which is 60, and the area that we don't know of the other piece, which would be A. So to set this up, that means that the 13 is squared and the 9.1 is squared. So 13 squared is 169, and 9.1 squared is 82.81. And so that is going to be equal to 60 over A, and so we can continue with solving. So 60 times 82.81 equals 4,968.6, and that's going to be set equal to 169 times A. But if we divide by 169 to get the A alone, we end up with an area of 29.4 centimeters squared. So basically the difference between finding a perimeter, which is in one dimension, right, and then finding an area, which is in 2 dimensions, is that we use the same scale factor, but when we set up our proportion for area, we need to square that scale in order to make it work with that new dimension. Alright, so then the last one here, we have ABC similar to DEF, these triangles. They're telling us that BC is 4 centimeters, EF, the matching side, is 12 centimeters, so they've given this side and this side, meaning the scale factor. And so the scale factor is 4/12 or 1/3. They're telling us that perimeter is 42 millimeters, and the area is 96 millimeters squared for the DEF, so this second one here. And so we need to find the perimeter and area of ABC. So again, notice that when they gave us the title here, they said it was ABC to triangle DEF. That means that anything involving triangle ABC is going to be in the numerator, and anything involving triangle DEF is going to be in the denominator. It does tell us that DEF are each of these measurements, and so if we use those to solve, that means that they're going to go in the denominator. So, in order to find the perimeter, as we did before, or that one dimension length, we still just need to use 1/3, but then set it equal to the fact that we don't know the one perimeter, but the fact that DEF's perimeter is 42. Then we cross multiply to solve, so 42 is going to equal 3 times P. Divide by 3, and we get a P of 14. And so 14 millimeters is the perimeter of triangle ABC. Okay. So then the next one is our area. Alright, an area, remember, is in 2 dimensions. So when we write our scale factor, we're going to need to square it. And then we can set it equal to its area over the area already given for the other triangle, which was 96. If we distribute that squared, we're going to get 1/9. And then we can cross multiply. 9 times A is going to equal 1 times 96. Divide out that 9, and we get an area of 10.6 repeating. And that is going to be in millimeters squared. And that's triangle ABC's area. So again, the same idea happened here. You're always using 1/3 or that scale, but if you're ever talking about area, just square that scale, and then you can solve the same way. Alright, so that's 7.5, and so you're going to use these ideas in your assignment to find some perimeters and side lengths and areas.